everyone. Now, before we even start our meeting, perhaps we would brief first for the forum of the day. Please mute your microphone if you are not speaking. And for the Q&A sessions, which will only be available for session 2, 3, and 4. And if there is any other pertinent questions that you'd like to bring up, please feel free to use the chat box to communicate with the event organizers. And there will be also a photo session at the end of the welcoming address. So please feel free to turn on your video for the session at that time. So let's start our event of the day. A very good morning to Engineer Academician Emeritus Professor Tan Sri Dato Dr. Chua Hian Teck, the President of the ASEAN Academy of Engineering and Technology, AAET, Professor Oh Yong Won, the President of the National Academy of Engineering Korea, NAEK, Senior Fellows, Associate Fellows, and members of AAET, and fellow participants of today's forum. Welcome to the 9th ASEAN-Korean Engineering Forum and Roundtable Meeting, co-organized by the ASEAN Academy of Engineering Technology, AAET, and National Academy of Engineering Korea, NAEK. I'm Chow Fong here. I'm pleased to be the moderator of the first session of today's forum. Ladies and gentlemen, this will be our 9th edition of the forum and roundtable meeting, and this will also be our second time for the forum to be held virtually via Zoom as well, due to the pandemic. So, fellow participants, today's 9th edition of the forum would be themed with climate technology and industrial cooperation toward carbon neutral in ASEAN and Korea. Now, this theme is aptly and timely in providing a discussion platform for ASEAN and Korea, especially the commitments made globally during the recently held 26th UN Climate Change Conference of the Parties, COP26, which was held in Glasgow last month. Now, countries committed themselves to further accelerating their decarbonization plans, as well as also reduction of global greenhouse gas emissions. Now, today, we will have 8 speakers sharing their thoughts through 2 sessions today, and there will be a Q&A session at each session, except for the session number 1, and of course, the welcoming address. Now, the 8 speakers today will be presenting their paper and of course reports as well on various issues on climate technology and cooperation between ASEAN and Korea. And it includes topics like water management for carbon neutral, the photovoltaics technology, the PV technology, and also the business and applications of the climate technology. Now, to begin with the day, let us have the opening addresses from both the co-organizers of today's event. And for the first welcoming address, we'd like to invite the AAET President, Engineer Academician Emeritus Professor Tan Sri Dato Dr. Chua Hian Teck. Now, a little bit on Professor Chua. He is a Malaysian eminent scholar, researcher, academic, and industrial leader. He is also a Senior Fellow of Academy of Sciences Malaysia, ASM. He is the immediate past president of the University Tunku Abdul Rahman, Malaysia, Utah. And he is also the former president of the Federation of the Engineering Institutions of Asia and the Pacific, FIA. And with this, I'd like to invite Engineer Academician Emeritus Professor Tan Sri Dato Dr. Chua Hian Teck, the AAET President, to deliver the welcoming address. Over to you, Tan Sri.
Thank you so much, Chow Fong. I hope you all can hear me.
Yeah, loud and clear.
Thank you to the moderator, Chow Fong, and also thanks to the organizing committee for helping to organize for the second time this roundtable meeting in the forum via Zoom meeting. First, I would like to thank NAEK, National Academy of Engineering of Korea, the President, Professor Kong Oh Yong, all his team members, all my old friends and new friends, and also friends from NAEK Korea, and also AAET fellows, associate fellows, and friends from the ASEAN region. First, on behalf of AAET, I thank all of you for taking your time off to attend this particular nice forum and also the roundtable in the afternoon. Well, I must say that COVID-19 actually has changed our lifestyle, including the way we conduct meetings and attending conferences. So although we are physically not been able to be together, but at least virtually we will be together and we will still explore all the possibilities of cooperation and collaboration for the two academies. I believe that sometimes the online meeting will also make us closer in the sense that we cut down on our travel time. And so we can attend all this from the comfort of the house or from the comfort of the office. I must say that this year is very timely. Although in the past we talk about so much about fourth industrial revolution, digitization, automation, machine, AI, etc., etc. But somehow the COVID-19 pandemic has fastened the pace. So it is no longer a luxury, but it is going to be a necessity. So for AAET, maybe I could briefly talk about AAET. AAET, we now have about 384 Hon Fellow, Senior Fellow, Fellow, Foreign Fellow, and Associate Fellow. All the 10 ASEAN countries are all represented. Of course, the top 3 economies will be from Malaysia, Myanmar, and Cambodia. All right. AET has conducted many events in the last 1 to 2 years, although we are still restricted by the international travel. We have the online meetings. We have also under the leadership from AET, our SecGen, Professor Yu Hong Tak has been involved in the joint committee with NAEK to explore all further possibility of collaboration. One of our flagship event is the Engineering Science Fair, which has actually gotten this year itself, the online one. I just got a report that more than 72,000 participants online attending all the conferences, the workshop, the demonstration, all for the sake of promoting STEM and engineering education. So I won't take much of the time because I know today we have a lot of speakers all touching on very important area of climate change, global warming, new energy, and also how we can work together in accordance to the 2030 UN SDG. So I would say that on behalf of AET, we thank NAEK again for all your support, and hopefully we can find more areas for actual cooperation and collaboration. I just want to end with a proverb that I learned from our African friends. They say, if you want to go fast, go alone. If you want to go far, go together. So I hope that ASEAN and Korea can work together, particularly with the new regional comprehensive economic partnership that has been signed between ASEAN, China, Korea, Japan, Australia, and New Zealand. With that, I thank all of you again for attending today's event. Thank you.
Thank you once again to Tan Sri Dr. Chua Hian Teck, which is always very good at sharing proverbs to end his speech. And once again, I'd like to thank Tan Sri. And a reminder to all, please feel free to just mute your mic if you're not speaking, and to actually ensure a smooth flow of our event today. Now, next, we would like to have the second welcoming address. And the second welcoming address is definitely going to be delivered by the NAEK president himself, Professor Oh Young-won. He is also the vice president of the Korean Federation of Science and Technology Societies. He is also the provost and the executive vice president of Hanyang University from 2011 to 2013. For this, I'd like to invite Professor O to deliver the welcoming address on behalf of NAEK. Over to you, Professor O.
Thank you. Very nice introduction. Good morning, ladies and gentlemen. I am pleased to attend the 9th ASEAN-Korea Engineering Forum. Although the pandemic hit the whole world heavily and we are all struggling to tackle different societal challenges, our collaboration was able to continue thanks to the long-standing friendship and sincere dedication from the both academies. I must mention that this meeting could not take place without the strong support from our honorable fellows of ASEAN Academy of Engineering and Technology and National Academy of Engineering of Korea. Especially, I would like to express my gratitude to President Chua Hin-taek to host the event during this hard time. Currently, as the global movement toward carbon neutral society is accelerating whole world effort to reduce greenhouse gas emissions, expanding investment in climate technologies such as new and renewable energy become a national agenda. To simply with the Paris Agreement, which will have take effect from this year, most of countries are proactively responding to global climate change. Accordingly, I believe the theme of this year, climate technology and industrial cooperation toward carbon neutrality in ASEAN and Korea, is very timely and meaningful. Also, I consider it a great achievement to conduct a survey on the demand of the climate technology and industrial cooperation and identify cooperation area between ASEAN and Korea. I hope this cooperation among representative engineers can contribute to sustainable society going beyond a relationship of exchanging policies and technical development. I believe our solidarity and cooperation are invaluable resources which we can build a brighter future for all. Thank you very much.
Thank you. Let's have a virtual hand clapping to the two welcoming addresses by the president of AET as well as also NAEK. Now, let's move on to our next exciting session, is the photo session. So can we get ready ourselves with the best smile of today? It's still in the early morning, so let's begin our day with a good smile and also good photo session. So can you all turn on your video? Don't worry, it will just be 10 seconds, maybe perhaps. Just put on your best smile, smile of ASEAN and Korea. Is the host ready to take the photo?
Yeah, I will take first
yeah.
page. Okay, now it's first page. And this is second page. And also the third page. And also fourth page. And
Of ASEAN and Korea. Oops.
okay, that's all. Thank you.
Okay, cool. NAEK, are you taking the photo as well? NAEK? Do you want to take a photo or you have taken the photos? Okay, I think Dr. Fogg has taken a photo. I think it's good enough. So thank you very much for the photo session. And now let's move on to our first session of the day, session 1. We will have two speakers, one from Malaysia and one from Korea. This first session will be on the demand for climate technology and industrial cooperation in ASEAN and Korea. Now, for this first session, there will be no Q&A, so it is just a presentation by both countries, and the Q&A session will only be starting from session 2 onwards. So let's start our first speaker of the day. The first speaker is none other than from Malaysia, Professor Dr. Lim Yun Sing himself. So let me just introduce him to the participants today. Okay. Professor Dr. Lim Yun Sing is a professor in the Lee Kong Chian Faculty of Engineering and Science, Faculty of Engineering Science, University Tunku Abdul Rahman, Utah. He is also the chairperson of the Center for Power Systems and Electricity, Utah, and also the executive editor-in-chief for the Journal of Electronic Science and Technology. Now today, he's going to deliver the topic on why climate technology in ASEAN and Korea. So I'd like to invite Professor Dr. Lim to deliver this topic on why climate technology in ASEAN and Korea. Over to you, Professor Dr. Lim.
Thank you very much, Hao Fong. Can you all hear me?
Yes, loud and clear.
Okay. Can I share my screen?
Sure. Okay. Yep, the screen is on. Maybe you can put on the slideshow mode. Still not in slideshow mode.
Hang on.
Is that okay? Okay, yeah. The screen is yours now. Prof. Lim, you can. Over to you.
Okay, thank you very much. Good morning to everybody. My name is Prof. Lim Yun Sing. Today I will talk about climate technology in ASEAN and Korea. I'm not going to talk about my research area. Rather, I will choose to talk about what I have done for IPCC reports. IPCC stands for Intergovernmental Panel on Climate Change. It is one of the very important reports for the whole wide world, and most of the governments in the world would refer to this report and then make appropriate policy for the agenda of climate change. And we work day and night to come up with the reports in collaboration with so many different people around the world. And now finally we come to the final draft. Of course, this draft is still confidential. We cannot release to the public yet, but it will be released pretty soon. And I will pick some of the important points and then share with all of you. Hopefully, by sharing the knowledge contributed from different researchers and experts in the world, we can work together to improve our climate change for the benefits of all. Okay, this is the first slide, and this first slide is showing the global net anthropology greenhouse gas emissions, which is showing the world greenhouse gas emissions. Of course, in our
IPCC, we even argue that do we need to consider other gases? Can we just consider CO2? Because CO2 is really the main troublemaker. But the thing is, after a few rounds of debate, then finally we just come to a conclusion. Okay, let us just look at the greenhouse gas emission and not just focus on CO2. And you can see that we are going to reach 60 gigatons of CO2 equivalent in 2019. And the graph here showing that the contribution of greenhouse gas emission by different countries. And initially you can see most of the greenhouse gas emission come from EU. Then slowly the greenhouse gas emission from EU start to be very stabilized, and you don't see any increase in greenhouse gas. And what contribute to the world greenhouse gas is mainly from China nowadays. Any participant from China? Okay, so so this is the trend now, and we need to think of a way to bring down this greenhouse gas emissions. Due to the efforts of renewable energy penetration in the past 10 years, you can see now the average annual growth in greenhouse gas emissions in the last decade is 1.3%, which is lower than the previous decade, which is good news. Okay, and this growth are very much, the greenhouse gas growth is very much to do with the population growth and the GDP growth per capita. And we have this COVID-19 pandemics, and this pandemic actually help us to reduce the greenhouse gas emission, because we find out that this COVID-19 pandemic led to a steep drop in CO2 emissions from fossil fuel and industries. Consumer-based CO2 emission in developed countries and ASEAN, as well as developed Pacific region, are higher than in other regions. Okay. Developed countries tend to be a net CO2 importers, whereas developing countries like Malaysia tend to be a net exporter. That is the situation now. CO2 come from which sectors? I have shown you the slide here. The CO2 emission come from different sectors, and mostly come from energy sectors. 34% come from energy sectors. Then the next will be from industries. This FOLU stand for agriculture, forestry, and other land use. And then we have transportation. Transportation contribute to 15%, and then the rest from buildings. And we have this picture here. This picture is very important. And why it is important? Because now we have many people asking, do we need to really go for full EV? And the answer is yes. Full EV is one of the effective solutions to bring down greenhouse gas emissions. Now we are using petrol cars, and you can see the amount of greenhouse gas emission is quite a lot. And one of the reasons is you get the emission directly from the vehicles. And of course, you get the emission from transporting the petrol and the fuels. That will contribute to some. Okay, and then what about a hybrid car? Hybrid car is a good way to cut down greenhouse gas, but not the long-term solution, because it still have a lot of greenhouse gas emission. And then finally, you can see the best will be full EV, and you don't get so much greenhouse gas emissions. And the main emission comes from the generating power plants. So that is the most effective solutions as far as transportation is concerned. Right. I put this picture here, and this picture is actually come from publications. This picture is the our network, electrical network in the future, and this is the neutral carbon network. That means it does not emit any CO2, right? This is a completely different power networks at the moment. The power networks that we have now has all these power plants. But this network here has some power plants, but it has some other thing as well. It has nuclear. We have the energy storage systems apart from the renewable energies, and we have to use hydrogens. Hydrogens will be transported to different areas through pipelines, and we also have CO2 capture, carbon capture technologies to capture any extra CO2 emissions. So instead of just dump into the environment, we have the technology to capture CO2. We also have biogas, all this biofuel, and this biofuel will be supplied to the point of consumption through pipelines. We don't use any transportation like big lorry to transport all these biofuels. So from now until the stage where we can have zero carbon electrical networks, we have to do a lot of work. Yeah, it is not just my research areas. We have to pay attention on other research areas. Like we have to cut down the cost of renewable energy. We have to cut down the cost of energy storage systems. We have to think of a better way to handle the waste from a nuclear plant, because nuclear plant is still a very clean electricity. Only problem is that we do not know how to handle the waste safely. And we also have to think of the way to cut down the cost of hydrogens, and many other things. Now, apart from all these technology developments,
Recording in progress.
there are some other aspects that we have to pay attention, right? And we tend to ignore other aspects, like, for example, how to transfer technology, how do we bring the innovation from one country to another countries for the benefits of the developing countries, because most of the innovation or technology changes happen in advanced country. And we cannot just rebuild the vehicles. Rebuild the research capability in the developed countries. Might as well we tap on the existing innovations and then bring it to the developed countries for the effective diffusions and transfer of advanced technology for the benefits of the whole wide world. So we have to take care of other aspects. And I put up some slides here, and these slides here are very important for us to take care. And of course, it will be beneficial to ASEAN and Korea. And how do we work together for better transfer of technologies for the purpose of bringing down the greenhouse gas emission in this region. And this technology change and innovation are very important because it is a key drivers for economic growth and social progress. And we have the innovations in climate change, climate mitigation technologies. This happened quite enormously in these recent years. For example, we have the implementation of PV and LEDs due to the innovations. But unfortunately, there are trade-offs in the innovations. Some of the trade-offs are great environmental pollutions and social equality, right? Some of you might ask, we are trying to promote renewable energy, and then why do we get environment pollutions? Do you know that when we build our wind turbines, we need the rare earth? And where do we get the rare earth from? From China. And mining the rare earth is one of the environmental pollution issue, because every year the pollution is so much just because we want to mine the rare earth. But we need the rare earth. Why? Because our mobile phone, our laptop, our wind turbines, all this really needs the rare earth. And rebound effect are another issue. Why we need to take care of rebound effects? Because if people tend to think that the energy comes from the solar or the wind and they are free, always available, we tend to be very relaxed, and at the end we tend to use a lot of energy. We are not trying to help the earth, we are making the earth even worse. So there is this rebound effects that we have to take care of. So at the end of the day, what we need to do, we must have effective governance and policy in place to overcome all these trade-offs and also the rebound effects. Nowadays, we do research, we do innovations. We just don't focus on our research or innovation alone. So we have to look at the whole picture, get the other players into the pictures. So we have this systemic view of innovation. This systemic view of innovation is to engage all the players like finance institutions, startup companies, working together with the research infrastructures, right? And also the research institutions, so that we can have a all-round developments of the technology and innovations. At the same time, we must have the indicators to provide the insight in the innovation process. We cannot just innovate, constantly innovate without putting any attention on other aspects, like for example, environmental issue and also the rebound effects. We have the systemic perspective on technology change, and this systemic perspective of technology change is about helping the governments or the policymaker to bring up the changes in our use of renewable energy or other clean energy sources, right? We now know that we have this feed-in tariff. Everybody know that feed-in tariff, and feed-in tariff is actually a demand pull interventions implemented and started off by the German government, and then the rest just use that example to accelerate the the diffusion and transfer of photovoltaic system in our countries. So we have to always think of a way to increase the penetration or the use of clean technologies. So the policy has some innovation as well. We have to implement or innovate new policy, and this policy can really bring up the green technologies in the countries, especially in the developing countries. Apart from thinking of the innovation in our policy, the policy to bring up all these clean technologies, we also have to identify what actually inhabits the transfer of technologies. What actually stop the transfer and diffusion of all these innovations? Any technological change is inhibited if technological innovation system function are not adequately fulfilled. That means our innovation system function must be adequately fulfilled in order to bring the technologies to the third world countries or developing countries. What are those technological innovation system functions? Those are the functions that can really bring up the technology into the right pace. For example, we need to build up the human resource. We need to get the people to know the technology, how to use the technology, and how to set up the technology, as well as to maintain the technologies. If any of those functions cannot be carried out effectively, then eventually any good technology change will not be possible, because any functional innovative technologies must be complemented with all the trainings, the knowledge-based development and other things. It has to come with some other things. It's not just the technology. It has to come with the knowledge. People have to know how to use all these things. So at the end of the day, international cooperation is very important, always very important. So we have a big section here, a section in our IPCC reports to focus on international cooperations. These cooperations make sure that we can build up the innovation capability, and then we can plan the development of technologies, and especially for the least developed countries. Okay. What about IP? We do research. We always want to file IP. Do you think IP are good for the penetration and diffusions of innovations? Some people say yes, it is good, because we can bring in the technology safely to other countries without any plagiarisms. But some other people think that it is not, because you have IP, people are very reluctant to use your technology. So this IP, there is a mix of feelings. What should we do? Do we always have to file IP, and then this is the way, IP filing is the way to bring in technologies to developing countries, but this is always a point for everybody to argue, especially if you want to bring the technologies to the least developed countries. If you have IP, the cost of technology is definitely higher, and then how do you handle this high cost? That is another aspect that we have to think of, and then trying to solve the problems. financial support for international technology corporations. We know that we have the technologies, but technology alone is not enough. We must have the financial support. And where do we get the financial support? We must work together with the financial institutions to support the international technology corporations. So maybe the banks have to come in to support. Nowadays, we have this research scheme. This research scheme is to get the government to fund some of the research projects. Government can fund, say, 50% of the whole research project, and the other 50% come from the university or any research institutions. This is the kind of schemes that many countries are moving towards. Okay. Digitalization is very important nowadays. We have the mobile phones, and these digital devices is important for communications and monitoring, as well as analysis of the data of the energy system for the whole power systems. But these digital devices also need to consume energy, and large amount of this digital technology can also increase the energy usage, right? So there is this rebound effect in this use of digital devices. So if we do not take care of these digital devices, the use of digital devices, there will be rebound effects. So how to solve these problems? The absence of adequate governance can really bring up this issue here, substantial, a lot of use of energy for the digital devices. So we have to put in the right governance to make sure that proper control of energy consumption of the digital devices. Here is the summary. Technology changes and innovation play a very important role. Systemic view of innovation should be the way forwards for the implementation of any innovations. International cooperations is important to stimulate the technological innovation system functions. Financial support is important. Digitalization is important nowadays, but then we have to implement the right measure to minimize the rebound effects. That's all for me. Thank you very much.
Thank you, Professor Lim from Utah on this topic on the climate technology. I think in his summary just now, he has also shared, and of course, today he's presented us with the potential technology innovation and challenges, and of course, looking at international cooperation, perhaps today, between ASEAN and Korea, the roles of IP rights, financial support by financial institutions, and of course, the last but not least, digitalization as well in climate technology. So once again, thank you, Professor Dr. Lim Yun Sing from Utah for delivering the first speech today on climate technology. Now let's move on to our second speaker. The second speaker from Korea is none other than Yong Ki-chung. Dr. Yong Ki-chung is the president of the Green Technology Center of Korea. He is also the director of the Research Planning and Coordination Division of the Korea Institute of Science and Technology, KIST, from 2017 to 2019. He was also the vice president of the Korea Nanotechnology Research Society, KONTRS, 2018 to 2021. Now today, Dr. Yong will be presenting on the summary of the AAET, NAEK, ASEIC, and GTC joint project. With that, I'd like to invite Dr. Yong Ki Chong onto the screen for his topic on summary of the AET, NAEK, ASEIC, and GTC joint project. Over to you, Dr. Yong.
Thank you, moderator.
Yep. Do you want to put on your screen now? Okay, sure.
Okay, it's my pleasure to be here to present a summary of the joint project carried out by the AAET and the NAEK together with the ASEAN and the GTC, aiming to find out the needs and issues of the cooperation in the field of the climate technology. I hope my brief summary will set up a framework for discussions in the following sessions. But these are the contents. I'll start with a background. The ASEAN and Korea Engineering Forum actually has been held 8 times since 2013. Yet, with real materialized cooperation activities so far, so this time we made a new approach to sort of change the status quo. So as for the theme, we chose climate crisis and carbon neutrality. As it stands, one of the most important global agendas currently and for the long years to come, as Dr. Lim elaborated on in the previous presentation. And additionally, we took a more systematic approach this time to finding out mutual interest in identifying specific cooperation issues. To do so, we carried out the joint project with a goal to identify specific cooperation issues within the field of climate technology. And for the last 6 months, the project actually consisted of questionnaire survey, expert group discussion, and today's forum, which we hope, lay the foundation for the follow-up activities in the next step to materialize the cooperation. Well, the project actually was planned, was implemented by the leading participants in such a way that ASEAN, representing expert of the connecting entrepreneurs, take the lead in the first part of the project, and the GTC, which is a government-funded Polish Research Institute on Green Technology, takes the lead in the second part, and AAET and NAEK supervise the whole project, and while networking high-level experts. And a large group of parties interested in the follow-up activities also participated in the project, and I'd like to take this opportunity to thank all the participants of the project. So let me move on to the questionnaire survey. A questionnaire survey was conducted online for the 2 weeks in September for the target group of AAET and NAEK members, entrepreneurs interested in ASEAN and Korean markets, and cooperation partners of the leading participants. The questionnaire was made up of 4 different parts, as you can see from the slide, and part on the personal information and part on the choice of the activities, priority of activities responding to climate change. And the third part was on the technological demand. And the last part is on the international cooperation forms and role and things like that. So starting with the part 1 on participants' information, a total of 156 professionals actually responded to the questionnaire. Respondents from the Korea and from the ASEAN countries were roughly about the same, adding up to about 90% of the total respondents. And in terms of work field, people from the technology commercialization and the business actually account for 1/3, and people from R&D for another 1/3. And we found about 2/3 of the respondents actually have working experiences of 6 years and more in the respective areas. In the part 2, actually, we asked the people to make choices of important activities for responding to climate change in each of the 4 different fields of activities, as you can see from the column on the left. So we found, as you can see, the policy making was recognized as the most important activity for international organization and for Korea as well, whereas increasing awareness was recognized the most for Asian and noticeably technological development for ASEAN-Korean cooperation. So another thing that we should notice is that policy making, in fact, was recognized the important activity over first and second priority, regardless of the field of activity. In the part 3, we asked people to rank the priority of demands for climate technology and the industrial cooperation. And as it turned out, the mitigation, out of mitigation, adaptation, and mitigation, adaptation, convergence, the mitigation was ranked at the top priority overall, and respectively in Korea and ASEAN and as well. As you can see from the weighted index in the table down below. So the climate technology classification system that we used for the survey actually originally developed by Green Technology Center, which was then accredited by the Statistics Korea, and it was further developed for international use by GTC and the UNEP-DTU partnership recently. So it has 3 different categories, as you saw from the previous slide, and 14 divisions and 45 technological sections. Oops, sorry. Okay, at the subcategorical levels, the renewable energy was ranked the most needed climate technology in the mitigation technology part. And out of renewable energy, the photovoltaic power was ranked the most needed technology. Well, as for the adaptation technology part, at the subcategorical levels, the water management was recognized as the most needed technology. Out of water management, water treatment was recognized as the most important, with slightly behind the water resource and the security and supply as well. In the part 4, we asked this question, the question which is written in the yellow box, regarding the expected roles in the Asian and the Korean climate technology cooperation. The Korea's most expected role for Asian is project operation manager, whereas Asians for Korea is technology provider. I think these should be taken into account in planning stage of any successful cooperation project later. We also asked this question regarding preferred forms of climate technology cooperation. As it turned out, multilateral cooperation as well as public-private partnership was preferred on Asian side, whereas intergovernmental cooperation as well as public-private partnership was most preferred on the Korean side. Well, these are the results. I must say that the present questionnaire survey has some limitations and is unable to produce results of a much statistical meaning and for further detailed analysis. Firstly, the number of participants in the survey was not large enough. Especially the participants were unbalanced with respect to work field and probably technological background to avoid some biased results. Secondly, the answers were incomplete. In other words, the participants did not fully complete the questionnaire in many cases, leaving quite a few questions unanswered. Thirdly, the questions are in some cases unclear. So definitions of the terms to describe work field and international cooperation firms was not clear enough for the participant to make definite choices. Given this limitation, however, we think that still the present survey results make sense and are compatible with the our experiences, field experiences, and the existing information. So that's we have to take into account. Following survey, we carried out expert group discussion to concretize the survey results through multifaceted ASEAN-Korean expert discussions on the most demanded climate technologies in mitigation and adaptation categories, which are photovoltaic power and water supply and sanitation. Expert group discussion on photovoltaic power was carried out under the leadership of Professor Dong-Hwan Kim. I think that he will join in the discussion session in the afternoon. And with 4 Asian experts and 2 Korean experts on board. To summarize major opinions, public-private partnership, multilateral cooperation, and intergovernmental cooperation were really suggested using actually international cooperation funds such as ODA funding. On the technical side, we find, as you can see, varying needs for slightly different, technologies. In the case of Myanmar, the representative of the Myanmar actually showed interest in developing distributed electric power system based on solar energy in off-grid areas, along with these policies and regulations related to them. In the case of Cambodia, the demand for vehicle battery charging with the solar energy was actually confirmed. And in the case of Malaysia, technological development, they proposed technological development, including field tests on the tropical environments. In response, the Korean representative said, Korean also require field test of Korean products on the various environments such as desert, cold wave, heat wave, and wetlands on the dire environmental conditions. So there is some match between those two, which you might want to consider later. And expert group discussion on water supply and sanitation was chaired by Dr. Jagyum Kim, also with 4 Asian experts and 2 Korean experts on board. To summarize major opinions, suggestions for the joint research programs for joint conferences to share the and communicate need and solutions. These might be, indispensable and necessary in the beginning stage of cooperation, and later they suggested a funding source to find a model to mobilize funds from the Korean companies for their ESG and CSR activities. On the technology side, we find a slightly varying needs, demands, but with some converging point. In the case of Malaysia, demand for the study of the organic decomposition and energy conversion technology for waste treatment was actually suggested, and they needed to share Korea's experience, particularly on polluted river purification. In the case of Myanmar, there was a demand for rainwater harvesting system and water management system, especially with emphasis on the purification of polluted water. As for Singapore, there was a demand on low energy purification to obtain drinking water from nature and the desalination technology. And in Korea, the experts actually proposed a water purification technology and a low-cost, low-energy application technology, respectively, for Malaysia and Myanmar. So there is one common keyword, purification of water, in the case. So to summarize the presentation of our questionnaire results, the most important area in climate change response activities in ASEAN and Korea cooperation is technology development. Also, the policy making was recognized as important, first or second priority, as you saw from the presentation. The priority demands on the technological side was photovoltaic power in the area of mitigation, whereas water treatment in the area of adaptation. And the most expected role of Asian countries from Korea is project operation manager, whereas technological provider on the other way around. So the most preferred cooperation forms of public-private partnership and the multilateral cooperation project. I will just skip the summary of on the expert group discussions part, which I elaborated during my presentation. So let me wrap up my presentation with some suggestions. In the in the lower part of the slide, I show a schematic diagram representing sort of a generalized procedure for international cooperation, especially with the developing countries for reference. So the first thing we do is analyze partner countries' needs, and then whereupon we design technical solution packages. In fact, what we want to and what we have been doing in the joint project is this part. So based on solid needs and the technical solution package, then we can plan project and the feasibility studies, which we may develop further the scaled up project later using international funds like ODA and the Green Climate Fund and the P4G and ADB and etc. So to do that, in other words, like I say, before we develop further, we need a very solid needs and technique solution packages throughout this joint project. And to do that, to produce tangible output, it is necessary. We need to delve deeper into the cooperation themes and approaches. I think that the AAET and the NAEK could take on the role of the initiating further discussions on developing joint projects. Thank you very much. I hope my brief summary of the presentation will help the people to seek out the cooperation, the themes and approaches in the sessions after. Thank you very much.
Thank you once again. Give a round of applause to Dr. Young for his presentation, as well as also Professor Lim's presentation on the climate technology. I think Dr. Young has also shared with us the comprehensive survey done earlier this year, and of course the results and the future, and of course the expert group discussion on PV and water treatment as well. So once again, thank you, Dr. Young, for the summary of the survey and of course the presentation of the outcome. And that ends the session number 1 for this morning. Now let's move on to session number 2. Now, session number 2 is the continuation, I believe, has been shared by Dr. Young on the survey as well. One of the key aspect of climate technology and industrial cooperation will be on water management for carbon neutral. So for this session number 2, we will have 2 speakers again, one from Korea and one from Myanmar. So to start off the session number 2, let's have the first speaker for session number 2. Now, the first speaker will be Professor Yong Nam Kong. He is actually the research professor from the Institute of Construction and Environmental Engineering at Seoul National University, Seoul, Korea. And he's also the vice chairman on Korea Water Forum, Seoul, Korea. He is currently the president of the Korean Society of Ultra Pure Water, KSUW. Today, he's going to deliver his speech on challenges and opportunities in mainstreaming and implementing the water energy nexus in Korea. Now, with that, we'd like to invite Professor Yoon to deliver his speech on challenges and opportunities in mainstreaming and implementing the water energy nexus in Korea. Over to you, Prof. Yoon.
Yeah.
Yeah.
Good morning, everyone. And my name is Eun Nam Kung, as introduced, and I'm currently a research professor at Seoul National University. Today, I'm going to talk about the challenges and opportunities in mainstreaming and implementing the water energy nexus in Korea. I have 2 parts. What is what we have done for last 40 years in Korea, and the second part will be what we are doing and will do in the future. As someone who hasn't been to Korea yet, and this a red dot is Korea, and it's Korean Peninsula. Korea is divided by North and South. South Korea is 52 million, and North Korea is 26 million. We are now in South Korea, okay? For last 40 years, the population growth from 35 million to 52 million, the economic growth and industrialization was so rapid, and our per capita income is now $34,000 US. Urbanization also had huge changes, and 50% to 93%. And most people live in city areas, not in rural areas. And climate change made our seasons a temperate to a subtropical. And there are huge changes in every aspect in Korea for the last 40 years. And a first part, what we have done in water and sanitation. And this will tell you what we have done in brief overview. Number 1, water resources management. For last 40 years, we built dams and reservoirs in everywhere in the country. We have 90 large dams and 17,000 reservoirs for agriculture. For large dams for drinking water and industrial water and a hydropower. So the water utilization rate from the rainfall from the sky and is 28%. And for your information, And a couple of years ago, I visited Ethiopia in Africa, and their water utilization ratio was only 3%. And we even though we have a similar climate and a rainfall conditions. The drinking water supply, we had built our first drinking water treatment plant in 1908, but for last 4 years, we had built more than 500 drinking water treatment plants, and right now the national service rate is over 97%. The other 2 to 3% are remote areas in rural and some island areas. So almost all the population served by a regular drinking water supply. And national drinking water standards, 30 years ago, we had only 30 items in it. Now we have 61 items. And we used to use a sand filtration for drinking water treatment. Now we are moving to advanced and a membrane technology for drinking water treatment. For a sewage treatment for sanitation, our first treatment plant was built in 1976. Before that, we didn't have any sewage treatment plant in country. Right now, we have over 600 so-called STPs, and it makes all the rivers and streams clean and safe. Okay, for the sewage treatment plant effluent standards, we have 7 items, and now the national service rate is over 94%. And the sewage treatment process moved from a conventional activated sludge process to a tertiary process to remove a total nitrogen and total phosphorus. This one single a slide will tell you everything. From 1978 to a year 2021, we moved significantly the number of standards and items, and we also make our regulation and very stringent. For example, BOD 40 years ago was 30 ppm. Now it moved to a 20 ppm, then to 10 ppm, and finally, right now it's 5 ppm. When you have a stringent regulation, you have to provide additional process to treat your sewage and further and further. And right now, when we started 40 years ago, we had only 2 items, BOD and SS. Right now we have 7 items, okay? It makes all the rivers and streams and clean and safe again. And if you look at this slide, and you can see how we moved from time to time and the stage of a sewage treatment process. At the beginning, we focused only on removal of BOD and SS, some organic materials. Then, after we finished the BOD and SS part, we moved to a removal of nitrogen and phosphorus to prevent eutrophication. Then, after it's done, we moved to a management of toxic materials. And again, at that time, we were able to reclaim the water from wastewater. Okay. And all this was possible due to the National Water Research and Development Program in Korea. We started in 1992 G7 projects, then moved to EcoStar project, then Eco-Innovation projects. All these projects, national R&D program supports the science and technology improvement and advancement, and made it possible for our water industry to support all the infrastructure development. And also policy and regulations and standards helped and to have a water and sanitation complete in Korea. We had 4 major rivers in Korea, and total daily maximum laws and policy was applied. And we also had a smart systems applied. We also applying a carbon neutral standard sewage treatment plant a process too. Also, via science and technology and innovation, we were able to do capacity building. We developed a human resources and institutional organization building too. And we also had a knowledge and technology advancement. We also had a physical infrastructure development everywhere, including a drinking water treatment plant and sewage treatment plant and dams and reservoirs and everywhere. Now, because we have, we talk about our past for 40 years, what we have done in water and sanitation, I will talk about what we are doing and will do for the future, water, energy, and food nexus. And there are just few examples. There are so many, but I just picked a very easy, simple cases for all of you. Number one, the security of water, energy, and food in Korea. We do have security issues in these three different areas. Water security. Due to climate changes, there are increase of flood and drought in Korea. And the other one, energy security. 97% of energy are dependent on imports. Only 3% are on renewable energies and hydropowers inside Korea. Okay, so we do have a significant a dependency on foreign imports. The other one is food security. Our food self-sufficiency rate is less than 50%. So if we have any climate issues and if we have any energy issues, we do have a food security programs too. Water-related disasters. We have the same as in other countries. We do have drought, we have heat waves, we have heavy snow, we have floods and typhoons, we have algal blooms too. We do have 4 seasons right now, but we are moving, as I told you, from a temperate to a tropical climate. Now, some examples of a WEF nexus in Korea. Number one, we have lots of hydropower dams. We are transforming these hydropower dams to a multi-purpose dams. In the past, this dam was used only for generating the electricity, but now it provides a water supply and flood control function too, in addition to electricity generation. The other one is a floating photovoltaic solar power, and we are applying in the dam water in Korea. Okay, and one of the largest so-called floating photovoltaic solar power is built in Korea and in Hapcheon Dam, and its power is size is 40 megawatt. Okay, and there are more floating photovoltaic solar power systems are constructing and designing now. Next one is a dam water cooling system, and we are using on a internet data center, which produce a lots of heat and energy, heat. And so we are using a constant dam water temperature to cooling the ITC center. Okay, in Korea. The other one is water and energy and food nexus, and which can be applied for smart farms. There are a lot of power plants in Korea, and they produce a lot of warm coolant wastes and wastewaters, and that is used for farming and fishery industries to reduce fuel energy cost. The other one is heat pump systems. the lower temperature in water supply is lower than air temperature in summer, but higher than in winter. We are using this temperature a difference, and by using heat pump to cooling and heating and the buildings and systems. Okay, this is applied into a Lotte Tower, which is the highest building in Korea. Until now, I showed some examples, but this is what we are doing and what we are doing in the future. There are a lot of a sewage treatment plant and wastewater treatment plant in Korea, and until now, we regarded those systems as a pollution eliminators, remove organics, nitrogens, and phosphorus, and micropollutants, etc. But now we think we design it as a product, a producer, such as biogas, heat, and fertilizers, and etc. Okay, including electricity. And the examples for the whole diagram tells you and what's coming and what it will be produced from the system. And this the lot of research and development are ongoing in these areas for resource recovery from wastewater treatment plant. However, issues and challenges in Korea too. And all this water and sanitation, and we do build our infrastructure about 30, 40 years ago, and the aging systems requires a rehabilitation. And also, as the demand for environmental quality is increasing, there are standards are getting stringent, and you need to put more facilities and more processes to the existing systems. The other one is to meet a carbon neutral goal in Korea, and we need to reduce the energy requirements and energy use, and make it more energy efficient systems for all the water systems. This is the last slide, and for opportunities for improvement in water and sanitation. We still believe a water demand management, in other words, a water efficiency is a big part to contribute to a carbon neutral system. So we need to work on more efficient water system. The other one is energy efficiency in water and sanitation. As long as there are a lot of energy required to produce water and manage sanitation, we need to improve the energy efficiency in those systems. We also bring 4R systems in water and sanitation: reduce, reuse, recycle, and recovery. Finally, with IoT and big data and AI, cloud, and etc., we are applying our smart management systems in all our water and sanitation and dam operation too. Okay, so far we have done a lot of things in Korea for water and sanitation in Korea. We did it and we made it, and we think we can contribute in ASEAN's water and sanitation improvement with our knowledge and our experience. Okay, thank you very much.
Thank you, Professor Yoon, for his speech today. And I particularly like the ending where he says that he did it for Korea, and now it's time for it to be done in ASEAN. So that is a very good ending as well. And of course, he has actually touched on the implementation of the water energy nexus, and of course, the new paradigm of resource recovery and opportunities for improvement. So let's move on. Before we move on to the next speaker, just like to remind for those who have questions to put up for the speakers, these two speakers for session 2, feel free to use the chat room to put up your questions, and we will get the speakers to answer them at the end of this session number 2. So let's move on to the second speaker for the session 2 from Myanmar. So maybe a little bit on the speaker herself, Professor Dr. Kin Nini Tin, who is the chairperson of the Water Mothers Organization in Myanmar. She is also the initiator of the Water Think Tank of Myanmar, advisor and expert member of HELP, the high-level experts and leaders panel on water and disaster that advises the Secretary General of the United Nations. And she is also a former chief of section for the Water Sustainable Management Sciences Division of UNESCO Paris. Today, Professor Dr. Keen will be delivering her speech on the latest development of water energy technology and how it can be implemented in ASEAN countries, especially Myanmar. So for that, I'd like to invite Professor Dr. Keen Nini Teen on the topic of the latest development of water energy technology and how it can be implemented in ASEAN countries, especially Myanmar. Over to you, Professor.
Thank you very much. Thank you to all AAET and also NAEK members and presidents. I'm very grateful that I get this opportunity to explain about the water management, the importance of water management in carbon neutralization. Please allow me to share the screen. And yesterday, because of our poor connection, I was not able to do it, but let me try now. If not, the AAET Secretariat will help me from Malaysia. Can you see my page?
We can see your screen. Maybe can you put on to the screen mode? Slide mode.
Slide mode, yeah.
Yeah, okay, slide mode, yeah. And also my apology for shifting a little bit of the title, different from the agenda. The content is not different, but in order to tune in with the theme of our forum, I try to capture the new trend of hydropower generation, opportunity for carbon neutral transition. So let me explain why it is. Actually, the content is the same. I'm talking about the hydropower generation, but now I try to concentrate on the forum theme, which is climate technology and industrial cooperation toward carbon neutral in ASEAN and Korea. So just to tune in with the theme, to reach to carbon neutral, can you hear me?
Yes.
Okay. To reach to carbon neutral.
Professor, your presentation is still not in the
Then I will need the AAET secretary.
Okay, sure.
Okay, I will help you.
Yeah, please, Dr. Fogg. Yeah, I'm going to stop my share.
Okay, yeah.
Okay, and I also open my presentation on second computer so that I can keep talking while Dr. Fogg is helping me from Malaysia. This is the beauty of online and the teamwork. Thank you. Thank you very much. So let me go back to the last sentence. To reach to carbon neutral stage, we need a strong will. Okay, we need a strong will and understanding that we must go through an orderly transition. Why orderly transition? I will explain in the next slide. And the good news is a wide range of flexible solutions already exist. The professor from Korea told me everything what we need, or maybe in next 5 years. So after next 10, 12 years, we may be developing very new things. But from now and 5 to 6 years, we are safe. The technology is there, and those provide the optimized and renewable energy. Also, in the very first session, the carbon emission is mostly from the energy sector. So in tackling the energy sector and getting the 100% renewable, that is our vision, it is the thing to do. And for ASEAN, we must do it. So then, let me explain what is an orderly transition. Yeah, the orderly, now we see our screen with all the text. Thank you, Dr. Paul. The transition involves in the transformation of the most important systems supporting our life and well-being, and that is energy and land use system. So if these two are disturbed, our daily life is disturbed. Last week, I have a lot of electricity cut off because summer coming in. And we are depending on the hydropower, then we have to withstand the seasonal variations and also variations of the water levels. So that will also come in the next slide. So what is an orderly transition is a means to avoid all these negative consequences altogether and achieve energy sufficiency with sustainability. So in this 2021 and beyond, everything we talk will be balanced and to strike for balance. So can I get the next slide, please? Dr. Fogg. Yeah. So the rationale is actually tuning into the background of this forum. I always wanted to do the idea of the forum itself and then jump into it, dance with it. Okay. So in order to dance with it, I would draw your attention for fourth slide, fourth bullet. The achievement of carbon neutrality is critical to de-risking and enhancing the competitiveness of businesses in both ASEAN and Korea. Earlier, when we talk about these, COP 12 to COP 24 we were more concentrating on government associations and governments. But later on, for 10 years now, it is more visible in COP26 that we all talk about inclusiveness and no one left behind. Therefore, private sector in ASEAN and Korea may be leading in the future hand in hand with the government, NGOs, grassroots, and individual like me who cannot stay still. We have to work and work and work. So the second, next slide, please. The contents. Here I want to explain that the hydropower generation. So I draw to the scope of hydropower generation, and I would like to explain about the new trend. A new trend is not talking about how much power we will do only. Yes, we have to talk about how much power we will generate, but then while doing so, what are the process, what are the key stakeholders, and the sustainability issue? Because we would like to use this energy, if possible, forever for next and next and next generations. So part one, I will tackle 4 aspects. Number 1, technological innovation. Number 2, engineering solutions. 3, new paradigm of social inclusion. And that we put it in the modeling and call decision support system. And there we can teach in 2 things. One is manipulating the data, and the other is not being so transparent and manipulating the model. And then when we go to the multi-stakeholder forum, we can also manipulate the audience. Therefore, I put the honest in front of the adjective in front of DSS what I'm talking is not only the set of computer models, simulation models, and also AI and machine learning. Not only that, there is an honesty, there is consciousness, and that is we call honest DSS. Then number 4 is circular economy approach. After these 4, if we can really do it, when we walk our talk, the 17 SDGs will be achieved by ASEAN and all of us, also Korea. So part 2 is to begin with a simple baby step. I propose one small research project. And part 3 is to recommend that all our research output be streamed into the policy making of various governments, our respective governments. May I get the part 1 elaboration, please? Next one, Dr. Falk. Next one, Dr. Falk. Yeah. In part 1, the energy landscape is in transition. The previous one, please. The previous, yeah. Okay, it is in transition towards more flexible and sustainable energy system. In the old system, it is not flexible and also never sustainable. So what we are doing is the latest development of and engines and storage are very important. So here I only flash the notion into the audience that when we talk about hydropower, not only thinking the big power plant, but also the decentralized power plants. The next one, please. Here I show the engine. It is made in China. So you will see GE at the bottom of the slide. So the technology is always there. The technology to make very efficient water energy from this turbine and everything. So you can go to the website and see all of these details. Next one, please. And in this part, I talk about the case study because I want to emphasize on off-grid and decentralization. Because in Myanmar, we always think about Lopita and we always think about centralized power generation. Then it goes to the central grid, national grid, and then people who are near to central grid got the electricity. Now, by decentralizing with all these technologies, I can assure the smallest village in the farthest corner of Myanmar or in Indonesia or Malaysia can get the electricity. And development index, human development index, also include the electrification. How much percent of electrification is available in that country? So that is what I'm talking about on this slide. The next one, please. I put full of text because to reduce the time of presentation, to maximize the knowledge transfer, I do in that way. So this is my references. So the solution is energy storage and optimization. So only 2 keywords, energy storage. So next slide, please. The energy storage, I can energy storage. I did not put the picture, but it is the continuation. It's like a big battery. Okay, so we have the telephone, our telephone. It has a battery. So if we produce the energy for one village, they will have the energy storage. That's what I'm saying. So this one is the aspect 2 energy engineering solutions. When we built the dam in Myanmar, We have so many dams, more than 800. But later on, we consider putting the fish ladder because we want to take care of environmental sustainability. But then there are arguments that how can we really evaluate the fish are okay and not dying? So this engineering solution, this one is a little fish. And that fish is 3.5-inch long and 1-inch wide, and the weight is only 43 grams. So in the next slide, how it works is this little fish go into the turbine and still getting out okay. You see, therefore, the environmental standards, EIA, SIA, and HIA, the health index, all these can be guided by the good policy, good regulation, and water law, something like that. And the technology and engineering solutions are there to reinforce these law. If someone say this cannot be done, this fish, little fish, mechanical fish, will prove that it can. Next slide, please. So this is the aspect 3. I have put this EIA, SIA process, how we did it in Naufa hydropower dam on the Selwyn, but there are 7 steps to go to check real EIA and SIA, but we were at stage 3. So this is not the theory. And if you see from my camera, you see, there you are. This is the pamphlet. We do it in 2019. But here, the key message is honest DSS, decision support system. It is to do with rainfall, to do with runoff and water level and the volume of the water and the head and the turbine, and then how much electricity we produce and the location. Then we go to the community and go to the potential affected people and explain about these transparently. Come back, get the input, go into the computer and decision support system, running again the hydrodynamic model and sedimentation model, we name it, all simulation, but inclusive of the social input and their concerns, environmental concerns, all social concerns. So this is the aspect 3, honest decision support system. Next one, please. The 4th one is the circular economy approach. If I can explain this slide, circular economy approach is different to our old style, the linear one. Linear one, we go to the forest, get the resources, do the product, and the product is sold and the waste is dumped. That is very straight line, linear. Now in the circular economy, what we do, we get the raw material and do the product. While we do the product, we do the least emission and we get the product, then the waste come back to the raw, either as itself or chopped off or reformed, or if it is iron, we remold it, etc., etc. So that is called circular economy. Therefore, if we do the energy generation, if we take care of these 4 aspects, we are definitely reducing the carbon emission, and we are closer to our vision, 100% renewable. Next one, please. And now is Next one, please, Dr. Fong. Next one. And here, oh, sorry, the previous one. I just would like to link how it is with the global movement, which is eco-civilization. Eco-civilization talk about the holistic view of our earth, human being, and the resources and the nature. So what we do is we get a lot of people to talk about it and start making the circular economy. Here is the website. So it is not a dream. It is not a hope. It can be done, and it is the ticket for our existence. Next one, please. So part 2 is a simple baby step, very small step, because we are in the project and our leader already explained about the project, the survey, the outcome, the experts' opinion, etc., etc., etc. So this is the big thing. But this one is the piggyback. If there is voluntary and passionate researchers from Korea, from ASEAN, please come forward. We can make a pilot project. We can look around ASEAN and see the dams and take a baby, it's our baby, and we make the research study under the framework of these 4 aspects. Okay, forget about finance, forget about everything, because idea is most important. Everything will follow. The next one, please. Then, are we really doing research for research? Are we really doing the research for policy? Actually, we are doing research for policy. And that is why in this struggle, we always have to convince our respective governments to take up our research finding. And of course, we need the finance, but once the policy is in place, the financing can be from many ways. The first is national budget, of course. The second is from private sector budget. And the third is from SDG 17, which is partnership and collaboration. And also a lot of multilateral donors. So what we do in the help is we try to explain what is to be done and why, because it is going to be the benefit of the whole mankind.
Professor Dr. Keen, you have
this is the
1
last
minute.
one. This is
1
the
minute to
last
wrap up
one.
your slides. Okay, thank you.
Yeah, this is the last slide. So earlier in this slide, you will see 90% of money is used in the emergency response. Then sustainability in 10%. And now we want to swap that. And why this slide is there is because, like our professor from Korea said, earlier we do the dams for electricity alone, agriculture alone, and now we try to put it multi-purpose. So the hydropower dam can be multi-purpose and also can help flooding. Okay, next one, please. I think this is it. Yeah, this is it. Yeah, so thank you very much. And I hope that we can do something on this thread. Thank you very much.
Thank you, Professor Dr. Keen, for her presentation on the opportunities and also the plans and for suggestions for the hydropower projects in ASEAN itself. So we have about 3 to 5 minutes left for the Q&A session. So I may just want to open to 1 or 2 questions, maybe one each to each speakers to answer on session 2, water management for carbon neutrality. So can we have any questions on the chat box if you have any to put up? So far, I did not see any so far. If you have any, perhaps if no, maybe I will just ask first Professor Dr. Keen from Myanmar. So what is your biggest challenge, do you think, in hydropower, in implementing the hydropower new trends that you have highlighted just now? What will be the biggest challenge to implement?
The biggest challenge is the understanding of the all stakeholders. And that is my biggest challenge. Because people don't want to lose their profit. And because of that, they want the status quo. When they want the status quo, they always go to the dam building cost-benefit ratio. And the cost is this much and the benefit is that much. So they are, without knowing, without bad will, without intention, they keep the status quo, which is linear economy.
Okay, thank you, Professor Dr. Keen. So my last question is to Professor Yoon. Just a quick one. You have highlighted on the success on the implementation of the water energy nexus in Korea. If you have the tagline, Korea can do it. So looking at the potential water energy nexus in ASEAN, which particular project which you believe can be a priority or the most viable to be implemented in ASEAN?
Well,
Professor Yoon?
all the examples I showed on my slide can be applied into ASEAN countries too. It's not really high technology, and you can easily apply all those a floating photovoltaic power system. Also, you can use a heat pump system, and you can use the cooling system too. So these are not really high technology and systems, and we use in everywhere if you can. And the other thing I just want to share with you is for last 40 years, we didn't have much water supply and sanitation until 1970, late 1970s, but for 40 years we built our infrastructure for water and sanitation very successfully, and we can share that experience and knowledge with all the ASEAN countries when needed, okay?
Thank you, Professor Yoon. Let me see if there's any other questions from the chat room. So far, I've not seen any. Perhaps if that, maybe one last message from each of the speakers today. Maybe we start with Professor Dr. Keen. Keen?
Yeah, my message to the audience and also to ASEAN and Korean. I really would like to request. All of you that we go back to the simple life and efficient life, and we all do the efficient production together with the private sector, but it has to be one goal, which is to sustain this mankind and this nature.
Thank you, Professor Dr. Keen, for the message. What about Professor Yoon?
Well, again, between developing countries and developed countries, and I think we need to have the SDG 6 goals to meet, which is a water and sanitation for all. And I think sharing experiences and knowledge is the key to reduce those gaps between developing and developed countries. And we are ready to help all ASEAN countries if needed. Thank you.
Thank you, Professor Yoon. I really like his message. Always is Korea can do it, ASEAN can also do it. So with that, I think because of the time, because we are taking a short break for lunch break, and we will definitely come back later. The second moderator will take over from me later, and now is the lunch break for Malaysia and Korea, and of course ASEAN as well. So we will come back at 1 p.m. Malaysian time, and some maybe a different time zone. So with that, I will end session 2. And once again, thanks to all the participants, thanks to the speakers, and thank you very much. Kamsahamnida, terima kasih, Kesudibati. See you again.
Thank you. Thank you very much.
Yeah.
Please come back at the same Zoom link using the same Zoom link. Thank you.
Good afternoon, everyone. Did everyone have a good dinner? Good lunch? I'm sorry. I thought it was a dinner already. Well, I will be a moderator for this session and the rest of the session. My name is Ji-woong Yoon, a member of International Relations Committee of National Academy of Engineering Korea, and a professor of public policy at Kyunghee University. Is everyone all on? All right. Okay, I can see everyone. All right. The title is photovoltaics. The photovoltaics technology are being developed to decrease our reliance on fossil fuels to produce electricity. Recent years have seen a significant development of a wide range of photovoltaics technologies and a widening of applications. So, let me introduce the first speaker, Professor Chung Kok-Kung at UTAR. Okay. Well, Professor Chung Kok-Kung will present a concentrating solar power technologies, right? Is it right, Professor?
Concentrating solar power technologies. Yeah.
All right. Well, it's all yours. Please give a great applause to Professor Kong.
So, yeah. Should I start? Okay, thank you for the kind introduction. So for me, my today topics, I will talk about concentrating solar power technologies. First of all, I would like to introduce what is concentrating solar power systems. Usually, solar concentrating power system use combinations of mirrors or lenses in niche applications, actually to concentrate direct beams of solar radiations to produce forms of useful energy such as heat, electricity, or fuel by various downstream technologies. So basically, there are two branches of CSP. So in general, we call it as a CSP. So CSP can produce thermal energy or photovoltaic conversions. So for the solar thermal, usually solar thermal we can produce in three methods. One is power tower. You can later I will explain more details. And then the second one is parabolic dish concentrators, and then parabolic trough concentrators and solar furnace system. So you can see from these pictures, okay, solar power tower basically are the system that has central power. Okay, you can see this is a very big systems. Usually you can see in Europe or in US, it's surrounded by all the heliostats, which is a tracking device, tracking mirrors. And the second one is a parabolic dish concentrators. So this also quite big. Usually it's big, quite huge structures, and it's like those radar, similar to the radar design, but it's used to focus on the sunlight. And the third one is quite common in the Middle East for the thermal energy power generation. Usually is set up in desert in US and Middle East, UAE or Dubai. It's basically is a trough, very elongated system of parabolic. The next one is solar furnace, which is used to focus with a huge parabolics. And also the other side is a helostat, which is a tracking mirrors that track the sun and focus at the parabolics you can see here. And then
excuse me, Professor Kwong. Can you
yes
switch the your view, because right now your view is the presenter's view, not the
oh okay
viewer's view. Right. No, it's still I think.
Is it okay now?
Yes, I guess this is better. Yes.
This is better. Yes. This is
Right.
better. Yeah.
Thank you.
Is it now? Is the slide?
Yeah, now it's better. Yeah, now it's okay.
Can you see the slide going, moving?
Yes, yes, we can see it. Yeah.
Thank you. Thank you.
Yeah.
Okay. So just now I just go through again the picture. So this is a power tower, as I mentioned just now, and the next one is a parabolic dish. Then this is a parabolic trough, and this is a solar furnace. And okay, because your topics is more on photovoltaic, so I will talk more on photovoltaic. We also have research on this concentrator photovoltaic system. So for concentrating photovoltaic system, usually we have a lens that is concentrating materials that focus the sunlight. It's like a magnifier glass that we use to burn the papers. But this is a bigger size and designed to focus on the solar cell. The solar cell is you can see in a larger zoom area. This is a solar cell. So what is the difference between concentrator photovoltaic and flat photovoltaic? Concentrator photovoltaic actually the system that need focusing use a lens, and the flat photovoltaic is that the photovoltaic we see made from crystalline silicon that put on the roof. And usually this photovoltaic work under one sun, 18 to 20% efficiency. For concentrator photovoltaics, the lab can reach 47%, but the commercial product is around from 30 to 40%. So the material for concentrator photovoltaic actually usually made from triple junction solar cell. So for triple junction, the material is a compound semiconductor. It can be usually made from indium gallium phosphide, the first layer, which is aimed to absorb the blue light short wavelength, then followed by the green light absorption of green light using indium gallium arsenide second layer. The last layer is the germanium used to absorb the infrared range. So this design is try to well match with the solar spectrums. The solar spectrum we have, the sunlight is ranging from 200 to around 2000 nanometers. So so the spectrum of all this almost can be absorbed by the whole 3 layers. The current existing commercial system, we can find it in US. This is a Fresnel system using Fresnel lens to focus the sunlight. So Fresnel lens is the lens that we use for last time our OHP projector to focus the project the light onto the screen. So basically it's a lens, but it's a very thin type of lens, and it consists of also a lens followed by the secondary concentrator and then the solar cell at the last layer. Usually this is a modular design. One set is one lens, one secondary, and one solar cell. So there are many of these, so it consists of array. But the cell and cell is very far apart. That's why we call it as a modular design. And because of the cell is very small size, so they can use a heat sink for heat dissipation. This design have some challenge because the lens need to be good quality and costly. And then the cell, because it's far away, one cell to the second cell is the distance is far away, so there is a resistive loss, the wiring to connect one cell to another cell. So this system is we can find in the US. The company is Harmonix, and we also have a trough design in Spain. This is the design parabolic trough, and the solar cell is arranged in a array, single array, and then the focusing is a live focusing. Then the second, the third design is a dense array. We can see from this parabolics, and then focus at the center. The central area have an array of solar cell. And this design basically has high concentrations, about 500 times, which is we call 500 suns. And because the cell is arranged in array, so cooling is an integrated system. And this use through assist tracking. And then the parabolic surface is considered one of the complicated design in this system, complicated structures. And the other one we can see is this is quite new, is in Australia. Okay, so this is actually basically consists of the heliostat, which is all the mirror can track in 2 axes. So they are quite a complicated control system to focus the light at the center, and the solar cell is fixed at the center on the tower. We also share about our research, what we are doing here in our university. This is our research team. We work also on the concentrator photovoltaic system. This is our design. And this surface is not parabolic because you can see the surface is not that deep. Parabolic is quite a curve. This is not a curve, but it's slightly changed in the geometry. To explain, we call this as a non-imaging dish concentrators. We basically use a simulation to study the geometry, use a computational method to find the geometry. Our geometry, we try to come out a geometry that we can produce a quite uniform sunlight, and also the focus spot at the center is a rectangular size and high concentration. So these are our simulation and experimental result. We can try to simulate the surface, produce illumination, use a ray tracing method, try to produce. You can see this is an image, the focus spot that we can produce. Compared to the parabolic is quite usually is quite circular, and that is not well matched with the solar cell. The nature of the solar cell is square or rectangular, but the image of the sunlight is circular, so the matching is not good. That will cause the losses. So we try to come up with a geometry that can match well with the solar cell. And the importance of uniform illumination also studied by many researchers. And these are this is our first prototypes from the small one. 88 sun, slowly increased to the bigger one, 25 meters square, and even bigger, 125 meters square. So these are how the work. The light is focused. Each mirror plays the role to focus the light. And the tracking also using 2-axis tracking. We call azimuth and elevation tracking. So this tracking system can move in a elevated direction, and also the direction which is this we call azimuth, which is about the zenith direction. And we use the tracking formulas. Why we use this tracking formula? Because this tracking formula we derive it ourselves. We call general tracking formulas. This formula has advantage. Even our column is not well aligned with this zenith, we still can track it accurately, because we allow the 3 orientation difference, and these 3 orientation difference can be determined in the tracking process, from this tracking process, we can determine, because initially we just assume it's well aligned. So we get the error, then we collect the data for a few days. And then from that few days data, we can determine how much variation. This is, we can do back calculation to determine it. And that's why this formula has advantage of allow the column not perfectly perpendicular. That is advantage of our formulas. That's why we come up this formula. And this is a image that we produce. We use a SAM scanner, optical scanner to scan, and then we found that the image is quite uniform and quite rectangular and match well with the solar cell. So after that, we fabricate the solar cell. Okay, this is our fabrications. And then we do the first data collection and we get the good result here. But the first result not as good because of the gap. That we can see that there is a gap. We can't do it so packed because of we need to put the bypass diode as the usual solar panel. So in that case, we come out with some idea to just bypass the gaps and using optical funnel. We call optical funnel that big entrance aperture and the smaller exit apertures. So these are basically the compound parabolic concentrators. So we will not go into too details on the mathematics, but this compound parabolic is well designed so that all the light hit on the surface can be reflected to the solar cell. That is our simulation. So we've done the simulation at 38 degrees. All the light with a certain angle up to 38 degrees. You can see all the light still can go into the solar cell. So the solar cell is just attached to the back side, exit side of the apertures. And this is a simulation result of the flood distribution on solar cell. So we basically put as array. Yeah, this is array, 1/4 of the array. Because it's a symmetry, so we only need to see the 1/4. The other side is exactly symmetry. And also, this is a solar cell we designed after that. And this is actual solar cell with the lens. So this is our design. This is our design and fabrication prototypes. And after that, we fabricate and tested here. With this, we can produce more power. The efficiency can increase. And for the bigger one, we test at a high concentration because high concentration can save the material of the solar cell. So we can test up to 1,300 sun. And these are our experiment result. The efficiency is 36.8% at the concentration of 1,242 sun. So each solar cell have different concentration ratio. We test each one, and then each one have a high efficiency from 34 the minimum to 37 maximums. These are the efficiency. So we test with a full complete modules. Okay, so the conversion can up to 30% in average. So other than that, CSP also can be used for daylighting system. So these are the demonstration how we focus the light and then produce the daylight. Use a fiber lead to the house so that we have a lighting. Another design is for solar furnace. We can focus to the parabolic and further focus, and then the temperature can go to very high. If you have a 2-stage of focusing, we can go to more than 3,400 degrees Celsius, and it can melt all the material we put in, even the cement, coal, metal, steel, and tungsten wire. And these are done in China by my supervisor and his group members. using the similar design focus and used to heat the space for space heating during the winters because the house is very cold during winter. We need the heating, so it can use for the space heating. They use a thermal energy for space heating. So thank you. I think just 20 minutes. Thank you.
Yes. Well, thank you, Professor Kwong. You are on right time, and well,
thank you.
Well, thank you for a wonderful presentation. Well, as a moderator, I would like to put the Q&A and discussion at the last. So what if we just move on to Professor Dong-Hwan Kim's presentation? Well, let me introduce Professor Dong-Hwan Kim briefly. He's a professor at Department of Material Science and Engineering at Korea University. He's also a vice chair of International Advisory Committee, International Photovoltaic Science and Engineering Conference. Well, today, Professor Dong-Hwan Kim will present the cases of Korea's renewable energy-related cooperation with Asian countries and lessons thereof. Well, Professor Kim, it's all yours. Let's give him applause. Thank you.
Thank you very much for your kind introduction, Professor Yoon. I'd like to thank the organizer of this symposium for inviting me to this important seminar. My presentation is relatively non-technical, so sit back, relax, and enjoy, please. Right? Okay, I will give you an overview of Korea's PV installation history and Korea's PV now, and I will introduce to you some of the Korea's renewable energy cooperation records, such as Vietnam, Mongolia, and China, as far as I could find the materials, and then some lessons that I could figure out, and then I will summarize at the last. All right, here's the very complicated looking slide, but the message is that the Korea government actively supported the R&D of the renewable energy, RD&D, especially from 2004. And this is the only PV installation record that I borrowed from my old presentation material that I presented in year 2008, I believe. So here you see that in the early 2000s, the installation in Korea is in megawatt range. But now, last year in Korea alone, 4 gigawatt was installed. And this year, about the same or more PV will be installed. So the cumulative capacity is about 15 gigawatt as of 2021 now, and the size-wise, Korea records globally 6th in the world. So you can say that in less than 15 years or so, the installation capacity increased about 100 times in Korea. Here's the first PV systems. I found this material in internet by internet searching. So Hwado and Hodo is in 1987 and 1988. So it's about total 25 kilowatt for 2 years installation period. And then they used French product and American products for panels, and other parts also imported from other countries. And then in 1995, the capacity increased to 150 kilowatt. So originally, the system capacity was designed to cover about 3 light bulbs per each home. So that's how they calculated the capacity. But soon the capacity was, overwhelmed by the demand. Anyway, the next one is Hodo Island. It's also a remote island from in Jeollanam-do area. And in 1991, this is 90 kilowatt capacity, but this is an historic system because the whole system was made in Korea, the cells and the everything else. So that's that. But now now the PV plant capacity increased to megawatt range, especially this Solar Shido project has 100 megawatt PV size. Compare, if you consider the size of Korea Peninsula and the population density, the 100 megawatt PV plant is so big. Anyway, that's one. So the trend is that the PV plant nowadays in Korea, like everywhere else in the world, the plant size is getting bigger and bigger. And then the trend 2 is Korea tries to find a space to install PV as much as possible. So the one solution Korea found is that the dam, the water surface. So we call that it's a floating PV. So it's a megawatt scale. So it's very fresh news that the last month they announced that 41 megawatt capacity floating PV. So they claim that it's the world's largest dam floating PV. So it's all Korean technologies, and they cover only 10% water surface. And it's a profit model is also interesting. They share the profit with the local residents. So the rest of the Hapcheon, Boryong Dam or Chungju Dam, the megawatt range floating PV. So they claim that Korea is the global leader in floating PV. So this is one area that we could think of a cooperation with Asian countries, I believe. Well, here before I elaborate on the cooperation cases with Asian countries, I show you the summary of the history of the cooperation with Asian countries. So basically 2 parts, a seminar or symposium, so academic information sharing part. The other part is the actual system installation. So you can see that mostly it's Korea, Japan, Korea, China, and some cases Korea, Mongolia. Academic information sharing was there before or during before the actual system installation happened. So this is some proceeding material of the joint seminar. This is a Korea-Vietnam joint project. You could see that this is between the 2 institutes, which is the Korea Institute of Energy Research and Institute of Physics in Vietnam. And you could see the records of the idea incubation to all the way to approval from Korea government is, it took only 5 months or so. So very speedy process. But I only could find the proposal of this project. And I heard that this project actually executed, but I couldn't find the report of it. So if you give me another chance, then I hope that I could find the material and introduce to you. Anyway, this is the job delegation between Korea and Vietnam, and mostly Korea took the part of system design and production and actual system installation. And Vietnam part, they take care of the paperwork, administrative work, and also installation land work. And the most importantly, they do the operation, and also they do the data collection and report. That's the job description. This is the Korea-Mongolia joint project. This is again Korea Institute of Energy Research. And then also the Mongolian part, it's MOFE. This is the Ministry of Fuel and Energy or something. So the budget is about 1 billion Korean won or so. So 1 million US dollar or so. So you could see, interestingly, the Korea participants, there are the companies, small companies, the manufacturers especially, and the DICE is the gas distribution company. Anyway, the expected outcome, you see, that also R&D element is there also. And then you see the project history, then this is also very relatively speedy process, you could see, from the incubation to all the way to the installation. And this is what it looked like. They intentionally selected a very remote area from Ulaanbaatar, so 900 kilometers away from Ulaanbaatar. So you can imagine how difficult it would have been, it should have been, for the Korean engineers all travel all the way to there, and then they transport all the materials there and do the installation. So this is what, you show the activities of the installation, and the local people participated in the construction. And then here's the young kid's face, the happy face. And then the opening ceremony, you could see the lovely pictures of young kids enjoying the electricity. But the electricity, the capacity was pretty small, total 8 kilowatt or so. So it covers only 2 houses by Korean standard. But the whole village, whole Seoul village enjoyed the electricity with the PV and wind combined system. Okay, this is the result of operation. And then here again, Korea-China joint project. It's a 2-year project. By the way, Mongolia project was also 2-year project also. So here, again, the Korea Institute of Energy Research and the Beijing Corona Science and Technology, that's a commercial company. And then some Korea's manufacturers are involved. So again, here, this is a remote area. This is a Tibet area. So the job delegation is about the same. The Korea provided the products and the installation technology, and actually we sent some engineers to monitor and help the installation. But the rest of the job was taken by China. So you see the date, 2005 April, all the way to August. So here are the some of the pictures and how they install the PV like that. And then, interestingly, they collect the data using and send it through a satellite to Korea Institute of Technology. This was done in year 2005 or 2006. Let's go back. Yeah, year 2006. Yeah. So at that time, this was very ambitious and pioneering work at the time. From the Tibet area, you use the satellite and you get the data, operation data of a PV system and a PV system of 100 kilowatt PV system. And then you analyze that in Korea. So that's the idea. So how? So there is the there's the vertical line, broken line. So on the left is China's responsibility. So they collect the data and send it through satellite transmission, and then from Korea Institute of Energy Research took the data and analyzed them. So here are some examples. So they installed the 2 inverters. So inverter number 1 performance is shown here. And then here's another example of in 2006 again. I want to give you the lessons that I could think of from the previous cooperation project. So joint projects usually were initiated via a joint seminar or workshop. So I want to propose that we want to have joint seminars, hopefully face-to-face, offline joint seminars, and discuss in more detail that and to identify the research area or cooperation area, and then we can start from there. Of course, some research and commercial elements, such as field data acquisition and reliability test, should be included, I guess. And then the rest of them is just just my suggestion. All right. So I will summarize my talk. So Korea's PV installation date go back to 1987 with a size of tens of kilowatt. But right now, the annual installation in Korea is about 4 gigawatt per year. Korea has demonstrated the PV system technologies up to 100 megawatt scale, and Korea is a global leader in floating PV systems. So this could be an area that we could think of as a candidate item for cooperation. And then I introduced the 3 projects or 3 cases of cooperation, of renewable energy related cooperation between Korea and ASEAN countries, Vietnam, Mongolia, and China. And then Korea, Japan, China, and sometimes Korea, Mongolia, joint seminars served as a platform for the cooperation projects. Okay, that's all. Thank you for your kind attention.
Thank you, Professor Dong-hwan Kim. Well, you are also on time. Well, let's move on to discussion now. The participants on Zoom are allowed to have and discuss and ask questions for anything that we have that was presented. And we'll also, after the Q&As, and we'll also hear some comments and answers from the speakers. Well, raise your hand, please. Anyone? Okay. Or you can leave on the chatting as a test.
I can use this mic. Is this on? Okay. Well, I have a question to Professor Kong about the concentrator system, concentrator PV. All right.
Yes.
So you mentioned that the solar cells, triple junction solar cells, and I wonder where you could find them, because these kind of solar cells are almost extinct now.
Yes, we bought it from Germany. It also can be found in Taiwan. I think Taiwan also produced this kind of solar cell. If you are interested, I can share material with you.
Thank you.
Yes.
Well, okay. Yes, I saw a text here. Who is this? Professor Kim? Yes, Kim Nini Tang, Professor. You can open your...
Yeah,
Yes.
thank you very much. Professor Kim from Korean University. He was calling for the joint seminar and joint workshops. For 2022 World Water Day, the actual World Water Day is on 22nd of March 2022. But we would like to make it earlier, like last week of February or first half of March with eco-civilization. I will put the URL here, and if you are interested to co-organize or co-host the event, because it is the same thing that we are going to invite the very famous water professionals and carbon neutral people. Our host will be eco-civilization.
I see. Okay. Well, thank you. Right. Any other comments or knowledge that you would like to share? Right, we may need a stretch after lunch. We're getting a little bit sleepy, huh? Yeah. Okay. Well, thank you for the information regarding the water forum. Okay. Right. So, well, if there isn't any more question or comment, what if we move on to the next session, right? So, we can get a short break after this last session. Okay. Our fourth session is about the business industrial application of climate technology. And this session, you can hear the practical examples of hydrogen industry in Korea and Singapore. Let me introduce the first speaker, Professor Jong-hee Han. Professor Jong-hee Han is a professor at School of Energy Technology, which was newly established recently in Korea. And he's also a director of the Institute for Hydrogen Energy. And he's the expert of hydrogen in Korea. Well, please give him an applause, Professor Han. Yes.
Thank you, Professor Yoon, for your nice introduction. Good afternoon. My name is Jong-hee Han from Korea Institute of Energy Technology, which is a very newly founded school we called Kentech. today, it is my great honor to have a chance to present presentation here, and thank you for having me here. Today I'm going to talk about a brief introduction of Korea's activity for hydrogen economy. And my presentation is like this. Maybe most of you already know about the situation of Korea in energy field. Korea has, not very easy situation in energy field because Korea consumes a lot of energy because our industry consists of energy consuming industry like chemical industry, steel making, automobile manufacturers, so on. However, actually we don't have any fossil fuel resources in our country. So more than 95% of primary energy we import from abroad. And so we emit large amount of greenhouse gas, especially carbon dioxide. In 2016, we are the 7th largest greenhouse gas emitter in the world. So we have to solve this problem anyway in the future. So our government set up a policy to drive our country, energy system in our country toward the net zero and renewable energy basis. So we have many, our government announced a lot of policies to reach that goal. The first one is Renewable Energy 3020 plan that aims increase of renewable energy up to 20% by 2030. But recently we increased the number to 30%. And also our government announced carbon neutral in this year. We will reach the carbon neutral by 2050. To get this carbon neutrality and renewable-based energy system, we have to have hydrogen energy. Actually, we need to store the renewable energy in some way, and also we need replace many feedstock and source of heat by hydrogen. So our government announced a lot of policy to have a hydrogen economy, that is hydrogen energy and hydrogen economy. So I will briefly introduce the status of hydrogen economy in Korea. This is our carbon neutrality scenario, and then NDC, that is the nationally determined contribution for the greenhouse gas reduction. Actually, by 2030, we aim 40% of reduction of greenhouse gas, and then by 2050, we will reach carbon neutrality. These policies include hydrogen in each plan. Our plan is 194 million tons of hydrogen will be used in Korea for every year in 2030. And in 2050, we will use more than 2,700 million tons of hydrogen. A very interesting thing is we include import of hydrogen. It is because our renewable energy is not enough to produce green hydrogen for ourselves, because we have a lot of demand of hydrogen in our country. So we have to have more green hydrogen. So we plan to import. And if you can see the second column and third column, the application of hydrogen, you can find industry. Usually hydrogen is used for the power generation for electricity and mobility application, like a fuel cell vehicle. But in the carbon neutrality scenario, we have application of industry. That is, we need feedstock and heat source from the hydrogen for the process of chemical steel making and so on. This is the very well-known hydrogen value chain or hydrogen supply chain. Our countries are Korea interested in this hydrogen. Most of the technology written here, we are interested in. The left side, it is hydrogen production. We have hydrogen production from the fossil fuel. We call that gray hydrogen. And then blue hydrogen means we capture the carbon dioxide from the process. And then green hydrogen, that means we produce hydrogen from renewable resources. So we use the electricity from the renewable energy, and then using that electricity, we produce hydrogen by water electrolysis. And then hydrogen delivery, there's many methods to hydrogen deliver to the demand place. But we are recently interested in the long distance, high density transportation, because we have to import hydrogen from other countries in which there's a lot of renewable energy, like Australia or other countries in Middle Asian and South Asia and many countries. So we are very interested in the liquid phase hydrogen carrier, like a liquefaction or LOHC or ammonia. And also we are very interested in the carrier ship. And then up to now, we focus more on the fuel cell for the mobility and then power generation. But as I told you in the last slide, we are interested in the industrial use of hydrogen. This is the policy, the major policy for the hydrogen economy. We call that hydrogen economy roadmap. This roadmap is announced in 2019. We have a target we aim by 2040. Actually, this from this roadmap, we aims about 6.2 million fuel cell vehicle production in Korea, and we aim the 15 gigawatts power generation for fuel cell in Korea. So the final goal, vision of this roadmap is to be a leader country in the field of hydrogen economy by 2040, and strategy to reach this goal. We deploy fuel cell vehicle and then power generation system first, and then the infrastructure to deliver hydrogen is built up, follow the deployment of the fuel cell system. To do that, we need to have a technology. So we invest a lot of resources to the technology development. Especially we focus on the hydrogen production, actually green hydrogen, and then delivery system. Actually, we are interested in the liquid phase storage and delivery system. And then mobility and power generation is still interesting in. And then safety, infrastructure standard are a very interesting field for the R&D. In the future, our hydrogen supply chain is like this. We import green hydrogen in the liquefied form, liquefied hydrogen or ammonia. And then we also, domestically, we produce green hydrogen as well as blue hydrogen. And then this hydrogen, through a pipeline or trailer goes to the demand place. And we can use the hydrogen to generate power, generate electricity, and then for the mobile application. Also, we use it for the steel making, chemical, and cement industry. So currently, Korea, now we deploy the fuel cell system very fast. So I write down the number is 50 of the passenger car, 15,000 and over. It is because the number changed every month. So it is not. It is meaningless. Write down the exact number there. So we have more than 15,000 fuel cell vehicle running around in Korea. It is the world's largest number. And then we have more than 600 megawatts power generation, fuel cell power generation system in Korea. And still we have a lot of demonstration program. We have a taxi demonstration, and also we have HRS, the hydrogen refueling station demonstration, truck and bus demonstration. And then we also have many hydrogen city demonstration in which we have we test the hydrogen delivery system, and then combined electrolysis, renewable energy, and deliver system, including application. And then industry, they try to develop the new product. The picture above is the mobile refueling station using liquefied hydrogen. In that truck, we have a liquefied tank inside, and then we can fuel the fuel cell vehicle anywhere it can go. And then we also have the drone, the hydrogen powered drone. It is already proved the distance and then flying time is much longer than battery powered drones. So what technology we are interested in this stage? As I told you, we are very interested in the green hydrogen. The core technology for the green hydrogen is water electrolysis. We focus on the three types of water electrolysis: alkaline, polymer electrolyte membrane, and solid oxide time. Actually, every type has a different TRL, but alkaline and PEM types of electrolysis. Our industry making a big system, and then they are in the demonstration stage now. And then we are working on R&D to improve efficiency and cost down and long life. And then for the storage of the hydrogen, we focus more on liquefied phase. We are working on the liquefaction of hydrogen, and then we are working on the ammonia, and then we also working on the LOHC, that is the liquid organic hydrogen carrier. Usually we use the organic material for the hydrogen carrier. And then we also developed the carrier ship for the liquefied hydrogen, ammonia, and LOHC also. And for the industrial application, we are very interested in this, hydrogen reduction steel making. Hydrogen is replaced. Hydrogen replaced the cokes, which is used as a reductor in the iron making process. Also, we are working on very interesting in the heat resources as in hydrogen in the chemical process, and then we also produce very interesting in process of feedstock for the chemical process. That picture on the right side, upside, is the electrochemical conversion of carbon dioxide into the ethylene, which is the very important feedstock for the chemical process. And also we are very interested in the hydrogen turbine. We think hydrogen turbine has their own market with and then it is not competition with the hydrogen fuel cell system, because larger size of the generation part is covered by hydrogen turbine. We aim the target number is of the efficiency is 63% for the hydrogen turbine. And also we are developing the new mobility, truck, tram, train, and construction equipment, and drones, and personal mobility, and so on. So many industry in Korea, the big company and small company, they are very interested in the hydrogen technology. Some of them, like SK, Hyundai Motors, already they have their own business in the hydrogen field for like a fuel cell power generation or fuel cell vehicle, and they have a plan to have the business of liquefaction, fuel cell refueling system, and electrolysis, hydrogen turbine, and so on. And small companies, they are interested in more on the material and component of fuel cell. That's the end of my presentation, and then let me briefly introduce my institute. My institute, the Cantech, is founded in this year, May 2021, and then we are in the Naju area, that is the south part of the Korea, and we focus 5 different energy area. Actually, our school focus on energy area only, and we have 5 special specified area: energy AI, energy material and device, hydrogen energy, environment and climate technology, grid modernization. So I'm in the hydrogen energy, and then we have, up to now, we have 5 professors. They are very specialist in the hydrogen field. And then we have 5 more faculty members will join in 2-3 months. So we will start with 10 professors next March. So we are widely open for the collaboration with other countries and other institutes. So if you want to collaborate, please contact me or anyone in our institute. Thank you for your attention, and I'm very happy to answer your question.
Yeah. Thank you, Professor Han. It was a very nice presentation introducing a variety of applications of the hydrogen. Thank you. Well, our last presenter is Professor Chan Xiu Hua, who's at Nanyang Technology University. Is Professor Hua here?
Yes.
Sorry.
Thanks for your kind introduction, and I'm going to share my screen. Okay, good afternoon to all of you. My name is S.H. Chan. I'm a professor and the president chair in energy at Nanyang Technological University. Today's my presentation is on hydrogen and fuel cell activities in Singapore. So you can see a number of logos here. These are the research activities actually carrying out at my institute. My institute has about 250 research staff, full-time equivalents, and we cover this broad areas, including hydrogen and fuel cell, battery, energy storage, buildings, maritime energy, renewable energy, solar in particular, and then wind energy, and last but not least, the electric vehicle. So it's quite, a wide spectrum of activities carrying out. I myself is the co-directors as well as the founding member of the Energy Research Institute. Today's my presentation will cover 3 parts. The first is on the background. Secondly is on the low carbon strategy and activities. The last one is hydrogen and fuel cell research activities at my university. So in the background, I will cover 2 parts. One is on the CO2 emission profile of Singapore. And secondly is how the government charting the low carbon future for this city-state. So this is Singapore's CO2 emission profile. You can see that Singapore produces about 53 million tons of CO2 every year. And this CO2 is actually contributed from 3 main sectors: the power generation and the industry, both taking up about 40% of the CO2 contribution, and the transport is about 15%. The rest is from the home, cookings, and buildings, etc. So here you can see that for the power side, the power generations contributed the CO2 is actually divided into the industrial, because this power will be directly used by the industry. Transport, like for example, our mass rapid transport using the electricity, buildings, lighting, air conditionings, and household, including ironings, etc., refrigerators, etc. So every year, the CO2 will increase about 2%. So you can see that with this number, by year 2030, we will reach 60 over kind of a million ton per year. So this is how give you the sense that what are the emission will be. So by 2030s, we will peak our emission at 65 million tons of CO2 equivalent. As just like I mentioned that with every years of a 2% increment, by 2030 we will reach 65 million tons if business is as usual. Based on the current projections, this will allow us to achieve a 36% reduction in emission intensity, meaning that the total amount of the CO2 produced divided by the GDP. So this will give us a 36% of the reduction, by 2030s based on the 2005 level. On the right-hand side, you can see that this is what we promise. We are committed to reduce the emission to a 33 million ton, which is about half of the values achieved in the 2030, right? So we are going to halve this, by 2050, and net zero emission as soon as viable in the second half of the century. So the mitigation measure went to power generation side, industry, transport, building, household, and the waste and the water treatment, right? So we will adopt the advanced low carbon technology, i.e. the carbon capture, utilization, and storage and use of the low carbon hydrogen, right? Mainly from the import. So, and another measure is the effective kind of international collaboration. This is very important. Example, through this international climate action, regional power grid and a market-based kind of a mechanism, right? So in 2019, we already started the carbon tax, right? With an initial rate of a very low of 5 Singapore dollars per tons of the CO2 equivalent. And by 2030, this number will increase to $10 to $15 per ton. Right. Next, look at the low carbon strategy and activities. So, Singapore energy plans, we call it a 4 switches strategy. This was announced by Ministry of Trade and Industry. These 4 switches are actually corresponding to the natural gas, solar energy, regional power grid, and emerging low carbon alternative. And each of these switch is corresponding to energy efficiency, renewable energy, energy management, and alternative energy respectively. Let's look at the natural gas. About 95% of Singapore electricity is generated using the natural gas, which is the cleanest of fossil fuels today. Natural gas will continue to be the dominant fuel for Singapore in the near future when we scale up our other switches, right? Government will help the GenCo improve the efficiency of their power plant. So that's why we focus on the energy efficiency, continue to use the natural gas, but improve the energy efficiency. Secondly is the solar energy. As you know that Singapore is a very small city-state. Our land size is about 720 square kilometer, which is very small. So we have a limited space for us to deploy the renewable energy, in particular the solar. And in wind energy, we have a very low wind energy with an average speed of less than 2 meters per second. At a coastal area, although the wind speed can be higher, but we are surrounded by all the commercial activities like the shipping, etc. So Singapore's most promising renewable energy source is actually the solar energy. Our first target is 350 megawatt peak by 2020, which is on track. And the second target is 2 gigawatt peak by 2030. And an energy storage deployment target of 200 megawatt beyond 2025. The third one is the regional power grids. Singapore will also explore a way to tap on the regional power grid to access the energy that is cost competitive. This could be realized through bilateral kind of cooperation at our ASEAN network or the regional initiative. The last switch is called the emerging low carbon alternative. Government is looking into emerging low carbon solution that have the potential to reduce Singapore's carbon footprint. And this include CCUS, carbon capture and utilization storage, and hydrogen. Power generation in Singapore account for 48% of the total energy, about half of the energy consumption, right? And contributed to 43% of the CO2 emission. Just now I have shown you the CO2 emission profile, and although it's 48%, but in terms of CO2, it is 43%. This is because we use natural gas for our power generation. Government has a plan to purchase 1.2 gigawatt of power by 2027 and another 2.8 gigawatt by 2035. So these two add up together is a total of 4 gigawatt from Malaysia, Indonesia, and Laos. And this accounts for about 30% of the total power need of Singapore. Right. On the other hand, the 2 gigawatt peaks of a solar PV installation by 2030 would account for about 5.6 of the annual total power consumption, because today we consume 52 terawatt hours, and this worked out assuming that we have 4 peak sun hours, in a day, and by taking into consideration over 365 days and divided by 52 terawatt, this is about 5.6%. If we ignore the increase in the power demand every year, because this is the current power consumption. By 2030, it will be higher. So purchasing power from the regional country and own power generation. So if you still remember, this is our switch 3 and this is our switch 2. Using the solar energy would contribute to about 35.6 of the total power supply. And this would mean that we still need to import the low or no carbon energy for the balance, because this is only 30%, and in actual term, this is actually, less than 20%, because, power consumption only take up 48% of the total energy consumption, right? And this slide is taken from a National Research Foundation, closing the carbon cycle in the power and power industry, as well as power and the industrial sectors with CCUS and hydrogen. You can see a 2 color code here, the brown and the green. The brown color code is the existing pathway. Yes. The brown color code is the existing pathway, right? You can see that currently is pretty simple. We are one of the 3 major oil refinery centers in the world, right? So in order to refine the chemical, we generate the CO2. One is the natural gas, direct use of the natural gas to supply the heat, and it generate the CO2 as well. And the other one is reformings to produce the hydrogen. One is for the oil refinery, and the other one is for the town gas for home cooking, right? Currently, it's pretty simple. We generate the CO2. In future, the CO2 will be storage or used to enhance the oil recovery, in the region. And also, the CO2 can pump and together with hydrogen, right? We can create the chemical products as well as the fuel products, right? To a Fischer-Tropsch process. And hydrogen will be mainly from the import to Singapore. As I mentioned that we have a limited renewable energy, ideally it's not direct connected to the grid, and we have to rely on hydrogen import from our neighboring country. And hydrogen can be in a liquid form, organic hydride, or ammonia, right? So this is how it works. And I would particularly like to highlight another one is currently we are pursuing this and explore it as one of the options for energy transition phase. That is pyrolysis, or we call it CDM, catalytic decompositions of methane. Essentially, natural gas is cracked into hydrogen and the solid carbon. And the solid carbon is mainly the graphite products, and it is particularly important for energy storage like battery materials. So promoting the hydrogen's activities, you can see that in 2005, we organized the first World Hydrogen Technologies Convention, right? So this is the first WHTC in 2005 organized in Singapore, right? And then in 2018, we organized another conference called Hypothesis, stand for Hydrogen Power Theoretical and Engineering Solution International Symposium. This is the European symposium, the first time brought to Asia and organized by Singapore. In 2018, the same years, we signed the MOUs, MOU signing between 4 hydrogen associations to promote the hydrogen activities. I represent Singapore, and you can see that Korea, Japan, and China, right? So we signed the MOU to promote the hydrogen economy. So last year, not last year, the year before last, 2019, we organized a workshop on studies about hydrogen import and downstream application for Singapore, right? And another one is with CSIRO, and this workshop will carry out in the Australian High Commission on accelerating the renewable hydrogen opportunity, right? So the organizer of this workshop is a KBR, which Singapore's Prime Minister Office engaged them as a consultant to develop a roadmap for Singapore on hydrogen's import and application. If you wanted to get to know more detail about the hydrogen and the fuel cell technology research, development, and demonstration activities in Singapore, you can refer to this paper published in International Journal on Hydrogen Energy. And I like to capture the timelines here. You can see that these are the developments of the hydrogen and the fuel cell activities since 2000. Because of there are so many bullet points here, and I like to highlight a few with a star. Look at the blue color one, right? So these are the industrials project, right? You can see that the Horizon Fuel Cell is the second company after Gas Hub, formed in Singapore, and then Rolls-Royce Fuel Cell System engaged EDB, Temasek Holding, NTU, and the A-Star to discuss on the hydrogen project. And in 2005, Enertech, which is a consortium form, and the government and the Rolls-Royce synced $100 million, to form a consortium looking at solar oxide fuel cell development. I think this, yeah. And then after that, we have an electro power system open at strategic base in Singapore, an intelligent energy setup Asian supply chain hub in Singapore, and the GIC invests 63 million in intelligent energy. So you can see that these are all the activities. And in terms of demonstration, you can see that in 2003, the first fuel cell maintenance facility set up in Singapore with the first BP hydrogen refueling station, right? And then the second hydrogen refueling station is in 2005, right? And then these are things like that, and I would particularly like to point out that, in 2018, study of hydrogen import and the downstream application for Singapore commissioned by Prime Minister Office under the National Climate Change Secretariat, right? So you can see some of the photo here. The first fuel cell vehicle maintenance centers, and then we have the first hydrogen refueling station in 2004. 2005 we have the second one, and then we have a 6 Daimler Chrysler, on Singapore Road since 2004. We organized the first World Hydrogen Technologies Convention, and this is 100 million investment. and this is a 63 million US dollar investment, right? With this one is with Rolls-Royce, and this one is with Intelligent Energy. The third one the third topic I would like to cover is the hydrogen and fuel cell research activities at NTU. I myself lead this initiative, and this part I will cover the overview, right? Snapshot of what has been done in the last 30 years at NTU, and then two technology that we wanted to highlight. Especially these are pretty important for Singapore to move to hydrogen economies in the energy transition phase. The first one is a catalytic decomposition of methane. The second one is ammonia cracking. So you can see this is a very busy slide. Over the last 30 years, we have been working on a wide spectrums of fuel cell and hydrogen project. Here you can see that we work on micro powers solid oxide fuel cell. The solid oxide fuel cell is built on a wafer because each layer is in a nano size. So only the wafer has that flatness that would allow us to build multi-layers on it. So this is a 1 square inch of the wafer containing 500,000 of cell and interconnected together. And the big one is 1 megawatt fuel cell, and this is a project we work with Rolls-Royce. And this is for distributed power generation. And in between, you can see that we have many activities. We not just the micro fuel cell, we also work on the mini fuel cell, work on the chargers, and work on the UAVs. We fly our UAV, we develop our 5 kilowatt combined heat and the powers. We work on the hydrogen on demand and industrial project. This one is interesting. This project is actually a collaboration with a European community, and it's led by German Aerospace Center, comprising CEA, ENEA, IFA, DTUs. NTU is one of them, using the solid oxide fuel cell and run it in fuel cell and electrolyzer mode. So this is a European project. And we also developed a methanol-based kind of a fuel cell system as a range extender for the vessel. And we also developed our regenerative fuel cell system. So this is interesting. In 2010, we built a bus in collaboration with Tsinghua University of China. And this is a hybrid bus, with 40 kilowatts of a fuel cell stack and 60 kilowatts of a battery pack. So this is a fuel cell bus is developed to ferry the VIP during the Youth Olympic Game. So our university was selected as a Olympics village. So we built a bus to ferry the VIP, right? So you can see the wide spectrums of the activities. Currently, we have a hydrogen fuel cell demonstration on Semakau Island, which is 8 kilometers south of Singapore. And we have a fuel cell vehicles, and this is outdoors, considered as a big outdoor kind of laboratories for technology demonstration. So in a nutshell, our hydrogen and fuel cell activities cover this 6 broad area. We work on the hydrogen carrier, MCH in particular, with Chiyoda, as well as ammonia as a carriers, and then turquoise hydrogen generation. And this one is in collaboration with ExxonMobil. And we have some project that the energy system design and the prototyping, and work with the vessel industry, the shipping industry. Of course, this is our bread and butters, fuel cell electrolysis cell. And we also work on the power to X, generating, the syngas, and the syngas can further convert it into methane gas or any kind of a hydrocarbon fuel. And the last one is the poly generation using the solid oxide fuel cell to achieve the heating, cooling, as well as the electricity generation. So as just I mentioned, I would like to highlight 2 technology. One is catalytic decompositions of methane. As we know that methane is a natural gas. We use the methane as a source of a turquoise hydrogen, right? So it is not blue, it is not green, we call it a turquoise hydrogen. And high values of solid carbon produced instead of a CO2. So by using this technique, and actually we are using low trace reactors, and you can see that these are all the catalyst particle, the gas coming in, and then the hydrogen gas together with unreacted kind of a natural gas will be produced. And the solid carbon will be go through a cyclone and the filter off, right? And the hydrogen together with unreacted kind of a natural gas will channel to our combined cycle power plant to burn it off, and the carbon can be used for this application, right? So hydrogen and unreacted methane can be fed to the combined cycle power plant for power generation with a reduced CO2 generation. And we develop our proprietary kind of a catalyst for this application. The next one is integration of an ammonia cracker into the solid oxide fuel cell. So this is a solid oxide fuel cell and this is a cracker. So this is how we integrate. We develop our own catalyst, and by integrating the cracker into the ammonia, we can tap the waste heat from the solid oxide fuel cell to crack the ammonia, right? So, and you can see that this serves as, a waste heat recovery. Imagine that we have a 10 kilowatts of ammonia in terms of energy rate feed to the this cracker, and at the exit it becomes 11.42, meaning that we have increased the heating values by 14.2%, and this heat is essentially recovered from the solid oxide fuel cell. So so this is a project, and 1 meter cube of liquid ammonia can run 377 hours at this power, 6.68 kilowatt. So you can see that by integrating this together, by making use of the synergistic effect, and this will really one of the useful application. Finally, I would like to conclude, right? Decarbonization effort is challenging for land-scarred and densely populated Singapore due to the lack of a space for deploying renewable energy. Energy security, energy equities, and environmental sustainability, or we call it energy trilemma, are tremendously important for all countries in the energy transition time, right? We are not looking at just to bring in the green fuel, but the affordability is important. And we also have to look at, from a short term to long terms, the energy security issue. To realize the ultimate hydrogen economy, hydrogen and its carrier has to be integrated into the energy plan as a new energy vectors. Thank you.
Okay. Well, thank you, Professor Chang. It was a very nice presentation, sharing your knowledge and what's going on in Singapore for the last 30 years. Well, now let's move on to discussion. The participants are free to ask questions and give comments. Please. Sorry? Oh, really? Okay, let me see. All right. Okay, there's in the chatting room, there's a question for Professor Chang, and it's from Abdul Hamid bin Abdullah. Well, he wrote that just now you said Singapore planned to buy electric power from Laos, and how are they going to transfer the electrical power from Laos to Singapore? So I think he's asking about the logistics.
Okay. Well, this actually is announced very recently. In November, we have annual kind of activities called SIU, Singapore International Energy Week, and government has announced that buying 4 gigawatt of power from the 3 countries, including Malaysia, Indonesia, and Laos. So this will through the yet to be developed kind of an ASEAN grid. So it may not be directly, connect from Laos to Singapore. It will go through Malaysia's or including the Thailand's and then reaches to Singapore. So this is underdeveloped. So I think that at high level, they have signed this kind of agreement to work together as ASEAN communities.
I see. Well, thank you. Thank you for the answer. Right. Any other question or comment? Yes, Professor Han.
Thank you for your great introduction of Singapore's hydrogen situation. Actually, I have two questions. The first one is, if I were right, please hear you. You said you produced hydrogen right now, and then in this stage you used hydrogen you delivered to the city gas. You mixed the hydrogen into city gas. Is it right?
This is, I think there are two parts. I think that let me address this question first. As I mentioned, that we have a very limited renewable energy. With the solar energy, 2 gigawatt peaks of a solar PV installation that will contribute only 5% of the total power need, or about 2% of the country's energy, because by 2030s, the power consumption is increased, and the power consumption only contribute to about 50% of the total energy need in Singapore. Because we still use the energy directly generating the heat instead of the power. So the power, as much as possible, it will connect to the grid. And for the city gas, most likely that we will import the hydrogen, and the hydrogens will mix with the natural gas in a certain percentage in order to achieve the Vox index that we want currently, so that we need not to adjust the valve, the flow rate, etc. So the hydrogen will be mainly, either is a liquid hydrogen form or carried by NCH, or in an ammonia form. And this is the plan for the futures to, use the hydrogens directly instead of our own reformings. Currently is that our town gas is reformed from the natural gas and then to generate the hydrogen, and that hydrogen mixed with the natural gas again to achieve the heating values that we want for home cooking.
So what is your target amount, percent of the hydrogen into the city gas then?
If you look at the current number, our town gas is about 41% to 60% of the hydrogen in terms of a volume concentration. 41 to 60. It varies in the range because it depends on the source of the natural gas, but average is about 50% of hydrogen in the town gas.
And the second question is, in a point of view of outsider, maybe electrical vehicle has more advantage in Singapore compared to the fuel cell vehicle. It is because the driving range is short, and the total area is not very big, or something more. So, but you mentioned about the fuel cell vehicle. So, you have any particular reason to continue the fuel cell vehicle?
Well, I think you rightly pointed out that Singapore is a small city state. I think if you look at the deployments, it will be mainly dominated by, battery EV. But having said that, we are also looking into logistic vehicle, taxi, buses, that would allow us to deploy the fuel cell vehicle. We are looking at a special kind of application, not for the passenger car. If you look at a passenger car, you need to install many hydrogen refilling stations. For taxi is different, right? For buses is different. They have their own station from point to point. So we do not need to invest a lot on the infrastructure. And taxi will easily, run, 300 kilometers in the day. So, you need not to charge it, every 1 or 2 days. For fuel cell, it can last, a single refuel may allow us to run, 800 kilometers or even longer. Depends on how many kilograms of hydrogens that you carry. Buses also will make more sense.
Yes, well, thank you for the answer. Right. I think we have more time. Well, last call. Right. Okay, well, if there, okay, one more question here. In the chatting room, what about incineration method to turn waste into energy? Is Singapore doing this method?
Well, I think this is an interesting and very good question, and we are amongst the earliest, get rid of the waste. Just now I mentioned the Semakau Island that currently we deploy. We have a project called REAPS, Renewable Energy Integration Demonstrator Singapore. Semakau landfill is 8 kilometers south of Singapore. It's actually the lands that when our waste is incinerated, and those inorganics kind of stuff bring to the Semakau Island for buried. So currently we are doing so for, not currently actually we have been doing so for many, many years. And many other countries now also follows Singapore's, experience, to get rid of the waste by incinerated them in the power, to generate the powers.
Okay. Well, thank you, Professor Chang, again.
Thank you.
Okay. Any question for Korean? Yeah.
Maybe I have one question for Professor Han. Thanks for the very nice kind of presentation. I would like to know that if your institutes also studies direct ammonia combustion in the gas turbine.
Actually, we not consider direct combustion of ammonia in the gas turbine. We consider the mixed ammonia with the coal in the coal combustion generator in this stage. It is because we have many coal combustion power generator in this stage, and then if we stop coal combustion generator in this stage, it is not easy for us. So
right.
We mix with the ammonia, and we reduce the carbon dioxide emission. So we are considering the mix with the coal.
Thank you.
But we are considering the direct ammonia SOFC, using the ammonia as a fuel directly to the solid oxide fuel cell.
Well, I don't know whether this is doable because if you are considering the nickel-based kind of a solid oxide electrode anode, it cannot tolerate higher than 0.5% of the ammonia. I believe that cracking process is involved, right? So ammonia is cracked to hydrogens and nitrogens, and then you applied it. I don't think that it can be directly applied because nickel cannot take the ammonias with a concentration of more than 0.5%.
Right. thank you for your good suggestion.
Okay, well, if there's no more question or comments, I would like to end this forum finally. Well, thank you.
Thank you. Thank you
for
so
all.
much.
And well, it was a very nice presentation and discussion of all the members and the participants of the 9th ASEAN-Korean Engineering Forum. Well, for those who are supposed to attend the roundtable meeting, please link through another Zoom link that has been sent to you already. Well, thank you for all the Professor Kim and Professor Han and Professor Chan and Professor Kong, and for the afternoon participation. Well, thank you all. Have a good day, and well, see you later.
Thank you. Thank you very
Bye.
much.
Thank you very much.